this is the 33rd lecture of the course MTH 204A for section B. Recall that from the last lecture that we were talking about primes in the ring of Gaussian integers, which we often call Gauss primes. So Z is contained as a subring inside Zi, and we have also talked about that. So the primes in Z, they need not be primes in Zi. For example, I mean, of course, we will give a necessary and sufficient criteria very soon, but just for an example, 5 can be written as 2 times I into 2 minus I. So that factorization immediately shows that, and none of these is units, so that factorization immediately shows that primes here need not be primes in Zi. They might admit some factorization. So we will try to see when a prime integer is going to be a prime in Zi. So early in the last lecture we proved the following. So I mean, I should put this as the main theorem, which has several parts. So first of all, so if this is a Gauss prime, this is a Gauss prime. Don't confuse this with your known pi, which stands for the ratio of circumference and diameter. Okay, so is a Gauss prime. Then pi times pi conjugate is either a prime integer or square of a prime integer. This is what in the last lecture we have proved, square of a prime integer. Now we will show that I mean the main, perhaps the first answer to the question we are dealing with. Suppose P is a prime integer, then so we can view P inside Zi as well. So if we regard P as a member of Zi, P is either a prime there, either a Gauss prime, of course I have shown this need not be the case always. For example, for 5 we have shown that, we have just seen that there is it admits a factorization. So what was the situation? It was simply from 2 plus I into 2 minus I, right. So either it is so this example suggests if this is not a prime, then it could be a product of a Gauss prime together with its complex conjugate. So Gauss prime, or it is of the form pi times pi conjugate, where this is a Gauss prime, this is a Gauss prime. Okay. So any prime integer, either that will be a prime in Zi, or it will be the product of a prime Gauss prime together with its conjugate. And then we do have the following. I will prove them, and of course this is already proved. I will prove the rest one by one. So so the situation is, as I said, that there are two possibilities: either it's a prime integer, either it's a Gauss prime. If this is a Gauss prime, then I mean then we are done with that, then we are done. Otherwise it will be of this form, and then we are trying to find when this will be the case. So for any integer prime, so this third part of the theorem indeed deals with that. For any integer, for a prime integer, for a prime integer P, the following are equivalent. So, what are they? Prime, pi is a Gauss prime. So, again let me remind you that the third part of this theorem deals with this situation, that when and only when this is going to be the case. So, therefore, we will give a list of 4 equivalent conditions. So, P is the product of a Gauss prime with its complex conjugate, equivalent to P is of the form a square plus b square for some a and b. Then third condition is there exists a in z, so that a square congruent to minus 1 modulo p, or in other words x square plus 1 is equals to 0 has a solution in z modulo p. Fourth one is p equal to 2 or p is congruent to 1 modulo 4. So, that is p will be 2 or the primes which are congruent to 1 modulo 4. I mean well, so I am not saying that any prime congruent to 1 modulo 4. Okay, so the primes, yeah, so the primes congruent to 1 modulo 4, 5 is 1, then another is 13, then 17. Okay. So, either p is 2 or any prime congruent to 1 modulo 4 will be, so any prime which any this even prime or any prime congruent to 1 modulo 4 will not remain a prime in the bigger ring Zi. They will be just the product of a Gauss prime together with its complex conjugate. Okay. And the fourth part of the main theorem. So, suppose p is a prime integer, yeah, integer which is also a Gauss prime. So, this theorem actually gives us a complete answer is a Gauss prime, then p has to be congruent to 3 modulo 4. Okay. Alright, let me prove them one by one. So, of course, the fourth one does not require a proof in view of the previous statements, because if p is a prime which is not a Gauss prime, then it has to be of this form by the second part of the theorem, and that immediately forces that p is either 2 or congruent to 1 modulo 4. Therefore, it shows that if p is a Gauss prime, then certainly p has to be congruent to 3 modulo 4. Okay. So, this is quite clear, and yeah. So, I think I should put it in this way. Let p be a prime integer, assume, then p is also a Gaussian prime if and only if, let us see, it will be if and only if, right, just check for a while. So, it is a prime integer if it is congruent to 3 modulo 1. So, certainly it does not fall into any of these, therefore, it has to yeah, so it does not fall into any one of this. So, therefore, this cannot happen. If this cannot happen, then it has to be a Gaussian prime. Yeah. So, this is in fact an if and only statement. So, now we will prove the second part of the theorem and the third part as well. So, for the second part it says that let us say p is a prime integer. So, proof of 2. So, proof of 2. So, p is a prime integer. So, we know p is a prime integer. So, what we do is let us consider p inside, let us regard p inside z modulo iz, and consider pi an irreducible. Let pi be a prime or irreducible divisor of p. So, what are we going to show? If p is a prime integer, then we are viewing p inside zi. So, certainly p is not going to be unit, p is neither 0 nor unit. So, therefore, it will have a prime divisor, be a prime divisor of p. Okay. So, that is p must be of the form pi times something that I do not care, but then one thing is also clear that pi prime that also divides p, right. So, pi prime that also divides p. So, therefore, one has p square equal to pi prime, then there is something. So, where pi is a Gaussian prime. Now, come here, if p is a Gaussian prime, then this is either a prime integer or square of a prime integer. Okay. So, therefore, what do you obtain from here? So, therefore, for pi prime, since this is either a prime or a square of a prime, so therefore, we can have only this or pi prime will be p square. We do have only these two choices in view of 1, and then let's now deal with the situation that if this is what happens, then like if you remember while proving this, so when is it like if pi is a Gaussian prime, when pi times pi prime became the square of a prime integer, that exactly happens when pi is a associate to. So, pi is, so I am just, if you recall what we have done in the proof of the part 1, so pi into pi prime becomes square of an integer prime. That happens only in the situation when pi is an associate to p. Associate to p. So, that is in this case p is also a Gaussian prime. Okay. So, this proves part 2. Now, let us come to part 3. The proof of 3 is also, so here the idea is that we take a prime divisor of p inside zi, and therefore, its conjugate also divides p. So, pi into pi prime will be dividing p square, since for pi into pi prime we know that either it is a prime or it is a square of a prime. So, therefore, we do have only these two options, and this option happens earlier we have seen only when pi is an associate to p, and that exactly yields what we want. Okay. For part 3, like it's a bunch of 4 equivalent statements. So, for part 3, so one thing is clear that this implies this, because pi will be of the form a plus ib, hence the product will be a square plus b square. So, proof of 3, 1 implies 2 is trivial. Okay, 2 implies 1 is also quite easy. Why? Because p is written as a plus ib times a minus ib. So, if these are not irreducibles, we can take, so if this is not an irreducible, we can take an irreducible divisor of that. So, therefore, it will be pi into pi prime times something, this is equals to p, and then it simply forces in view of this that either it is a prime in view of 1, either pi into pi prime is either this is a prime integer or a square of a prime, and so from that it easily follows that one must have equal to pi into pi prime. Okay. So, the equivalence of 1 and 2 are now done. Okay. The equivalence of okay, I think it is better to prove this, prove the equivalence of 1 and 3, that may be a better idea. So, we are now going to prove. Okay. So, for that we need the lemma. So, it is a very general observation. It says that suppose p is a prime integer, suppose this is a prime integer, then the following are equivalent. What are the following things? Maybe I should write A, B, C. P is a Gauss prime. P is a Gauss prime. This ring is a field. And part C is x square plus 1. If we consider this polynomial over the field z modulo pz is irreducible. Okay. Let me first prove the lemma, then in view of the lemma this will be automatic. So, this is quite clear that P is a Gauss prime means this will be, so Zi is a PID, so therefore primes are irreducible. So, if this is a Gauss prime then it is irreducible, and we are working in a PID because it is a Euclidean domain. So, then this ideal is going to be a maximal ideal, hence this is going to be a field. So, again let me repeat the argument. So, this is a maximal ideal if and only if, since we are working in a PID, this is a maximal ideal, this principal ideal if and only if the generator is a irreducible, and irreducible is same as saying prime here. So, therefore, the equivalence of A and B are obvious. Now, the equivalence of let us say B and C. Okay. So, for that we just have to observe the following thing, that yes, this is a very simple observation. I should put it like this. So, the justification I am leaving to you. You just have to what has been told to you earlier. So, we consider the map that sends each polynomial fx to the evaluation at I, okay, and the kernel of, so this is a homomorphism from zx to zy. Kernel is the principal ideal generated by x square plus 1. To see that, what you should do is you should rather get into this, you should rather extend this homomorphism to qi. So, here it is, since it is a PID and it is generated by, and x square plus 1 is an irreducible polynomial over qx. So, once the principal ideal contains an irreducible element, it has to be the generator. So, every coefficient, every polynomial with rational coefficient that goes to the kernel, that is, which has I as a root, as a complex root, it must be a scalar multiple of x square plus 1. Now, once it comes to zx, so x square plus 1 if divides a polynomial here, if divides a polynomial with integral coefficients inside zx, then it has to divide that inside. So sorry, so if a polynomial is divisible by x square plus 1 inside qx, then it has to be divisible inside zx as well. So therefore, like just passing that to extending that to qx, from that it is quite clear to us that the kernel of this map is this. Okay. So therefore, this is the isomorphism that we do have, right. Now what is, if we take the principal ideal generated by P here, what is going to be its image here, the pre-image. The pre-image of P is, basically the ideal generated by P and x square plus 1, this is the ideal inside Zx, okay. So therefore, Zi modulo this P is same as this quotient, okay. So this is a very general observation. Now in order to, now we have to analyze this quotient ring, and that is actually easy. I may simply remove this part now. So by means of this isomorphism theorems, it is now quite clear to us that this quotient is indeed isomorphic to, so this x square plus 1 quotient, the ideal okay, just the second this third isomorphism theorem, and okay, sorry, I think the order is to be reversed. Zx modulo, yeah, so Zx, this is x square plus 1, yes, so x square plus 1 would be there, I think this. Now let us see whether that works or not. X square plus 1 modulo this, and so then this will be simply isomorphic to, so this, the whatever is appearing here, isomorphic to simply z modulo pz x, okay, because this ideal generated by P, it is basically the set of all polynomials with whose coefficients are divisible by P. Now we have already proved that Rx modulo Ix is isomorphic to R modulo Ix, from that this will be isomorphic to this, and followed by, so okay, let me just explain orally. The proof is not at all difficult. So this part, this is isomorphic to, I think I should erase these as well. So the quotient ring that we are dealing with, whether it is a field or not, that ring is exactly isomorphic to this. So it is the quotient of this by this. So what is this? This is isomorphic to okay. So therefore you see that, and now what is this inside what is this inside this z modulo pz? This is basically the ideal generated by x square plus 1 in the polynomial ring over this field, right. So this is nothing but the ideal generated by x square plus 1 in the polynomial ring, of one variable over this field. So therefore it is going to be a field, therefore this quotient is going to be a field if and only if the ideal generated by x square plus 1 inside z modulo pzx, whether this is a maximal ideal or not, okay. I repeat that our concern was whether this is a field or not. So this is going to be a field if and only if this ideal generated over there is so this ideal is a maximal ideal or not, and this will be a maximal ideal if and only if x square plus 1 is irreducible, okay. So therefore the equivalence of 2 and 3, so this was already done, now this is also done. Okay. So the main point of this proof is you just deal with the quotient properly. First you identify the quotient identify Zi modulo P as a quotient of this polynomial ring, then you see that the ideal is generated by two elements. So you go step by step. So this will be simply first you quotient by this and then you further by this, and this is isomorphic to that. So by means of that isomorphism you see that this by means of this isomorphism, that between this and this you see this ideal now maps to the principal ideal generated by x square plus 1 in this polynomial ring, and this is irreducible, this is maximal ideal if and only if the generator is irreducible. Okay, so it is therefore the proof of the lemma is now over. I should now move for the desired equivalence of 1 and 3. So P is a Gauss prime. So if P is a Gauss prime, so the negation of P is that P is not a Gauss prime, right? Because for P we do have only two possibilities. So this means P is not a Gauss prime. Therefore, in view of this equivalence, therefore x square plus 1 is reducible over this field. This is a quadratic polynomial, monic polynomial. It is irreducible means certainly there will be a root, right? So over a field it is a polynomial, it is a monic polynomial. It is irreducible means certainly it will have a root, and the root A. So therefore we have, so 1 implies there exists a root. So there exists A in Z modulo Pz such that A square plus 1 is 0, which is basically saying as for the integer modulo P. Okay. So thus this part this 1 implies 3 is so 1 and 3 equivalence of 1 and 3 is equivalence of 1 and 3 is now over, because on the other hand if there is a root here, then of course this if there is a root here, then P is not going to be a Gauss prime, and that implies P has to be this. Okay. So equivalence of 1 and 3 is over. Now let us try to prove the equivalence of 1 2, then 1 3, that also we have done. Now let us do the equivalence of 3 and 4. 3 and 4. For 3 and 4 again we need another lemma. So these are actually quite elementary lemmas. Suppose that okay. So this new lemma says is an odd prime integer, then A, this multiplicative group of the field. So I think the proof of the lemma I should leave you as an exercise, because very elementary, has an element of order 4. If and only if P is congruent to 1 modulo 4. Okay. Why this is true? Because remember that this multiplicative group is a cyclic group of order P minus 1. So cyclic group contains an element of order 4 if and only if 4 divides the order of the cyclic group. And then the second thing is A belongs to Z. So A square satisfies this congruence relation if and only if its residue in Z modulo Pz has order 4, that is also quite clear. Okay. Because if a square is congruent to minus 1 modulo 4, then a to the certainly like a cannot be 1, right, certainly a cannot be 1, and therefore its square is certainly going to have, so a to the power 4 is going to be 1 modulo 4, and that is exactly what you want. So like the proof of this the statements of the lemma, proof of the statements appearing in this lemma, the proofs are very easy, and mostly I have given you the argument, and the rest if some small things are missing, maybe some direction and equivalent statement. So like I am leaving that to you to fill up all the details, but the main point is that here you are working with a cyclic group, and this is also like obvious one anyway. So since I do not have much time, I will just use that here to conclude 3 and 4. So like we can directly use that so congruent to sorry, this will be simply P, yeah, this will be simply P. Okay. Now you see that this, so if this happens, that's equivalent to say that this has some element of order 4, okay, and this element of order 4 if only P is congruent to 1 modulo 4, and when P is 2, it is always there. So in view like well, let me do very clearly. So like if this happens, then of course when P is 2, 1 is a root of this congruence relation. So therefore 3 happens, that enforces either P is 2 or this lemma directly applies here, and that settles that P has to be 1 more congruent to 1 modulo 4. This is the one direction, and on the other direction. So if P is 2, then of course we have a solution here, and otherwise if P is odd and congruent to 1 modulo 4, then from all these equivalents you have some A such that A square is congruent to minus 1 modulo P, that is exactly what you want. So 4 to 3 is also quite clear. So you see these are just the consequences of this lemma, whose proof is also quite easy. So with that I think this so thus we have a very complete picture of Gaussian primes. So like since as I said, it is very interesting to ask that in this ring extension Z to Zi, whether the prime integers they remain prime or not. So that question is now having a very complete answer, that that it is not going to be a Gauss prime if and only if either it is not a sum of 2 square, or like we do not have a solution for this congruence relation, or in terms of modulo it is yeah. So it is not going to be a prime if if it is if P equal to 2 or it is congruent to 1 modulo 4. Okay. So the question that immediately we have started with, that which primes will remain prime in the bigger ring, that question is now completely answered. Okay. So I think with that I should end the discussion of Gaussian primes, and let us move on to something else which is also very important in our context. This is called integral dependence. So I hope hopefully I will be able to finish what I want to say there today. Integral dependence. So Okay, for the rest of this lecture or maybe in the subsequent lectures, unless otherwise stated, we always assume all the rings that we are dealing with are commutative. So here we have, let us say, A and B, two commutative rings, and A is a subring of B. Okay, so this is not the setup we have, and let me also introduce a terminology that we say B is finitely generated over A, B is finitely generated over A. So this bigger ring is finitely generated over the smaller ring if over the subring if there exists x1 up to xn in B which acts as the generator. So what I mean by this is very simple, such that for every x in B there exists R1 up to Rn in A, so every x can be written as a combination of these elements. Okay. So it is analogous to that of a spanning set in the vector space. So every element of this bigger B can be written as a combination of just a analog of linear combination of elements of this n elements. Okay. Now let's define the notion of integral dependence. As I have already said, our setup is we do have two commutative rings A and B. As I said, we have two commutative rings A and B. And A is a subring of B. Okay. So we say alpha belongs to B is integral over A if, well, before giving the definition, let me first tell you some examples, some concrete examples that we have already seen, and that will immediately tell you how to formulate the definition. Recall that we are already familiar with these rings Qi, let us say, and also this C, C or maybe of course Z omega. Okay. So like, and in this example, let us say if you take I from here, so I is the root of a monic polynomial with integer coefficients, namely x square plus 1. So therefore there is a monic polynomial over Z. So here we simply take, so there is a monic polynomial over Z whose root is I. The similar thing happens here, happens there, and this is also, so here omega is some root of unity. So therefore there is a monic polynomial with integral coefficients which has lambda, which has this omega as a root. So now what we are going to define is we are going to define, we are going to define such in general terms, in the generality what such an element is called. So the phenomenon will be, yeah, so the what we want to write is, we say this is integral over A if there exists a polynomial, or I should maybe I can directly write that, if there exists A0 if there exists a natural number n and such that alpha to the power n So, that is, I will say alpha is an integral over A if there is a monic polynomial with coefficients over A, coefficients from A whose root is alpha. Okay. That is, if alpha is the root of a monic polynomial from Ax. Okay. That is, alpha is a root of some monic fx belonging to X. Okay. So, you can immediately see that like what this is nothing but the general, this is so this terminology is basically that includes all these examples. Okay. So, this is you can immediately see, as I before giving the writing down the formal definition, as I told you that we are going to generalize. What we are going to do is we are going to generalize these notions, that is the elements which are the roots of some monic polynomial over the smaller ring. So, this is the generalization. So, we say the alpha is integral over A. So, therefore, you see the immediately you get the examples here, that I is integral over Z, I is also integral over Z, or you can take I is integral over Q depending upon the rings that you choose, and here C, I is integral over R as well, omega which is root of unity, that is also integral over Z. So, these are the like very immediate examples of elements which are integral over the smaller ring in an extension of rings. We are now going to have some equivalent conditions for an element to be integral. So, those equivalent criteria will be of very much help to us. So, the following are the equivalent. What are the following statements? First is, so given that this is, as I said, this is our already set up, and we have B and alpha in B. So, the following are equivalent. So, alpha is integral over A. The second thing is A alpha. So, what is this? So, smallest subring of B containing A and alpha. So, let me say a few words about this. So, given any extension of rings, forget about whether any element is integral or not. If you take an element, let us say from the bigger ring, the smallest subring containing the bottom ring, and this element is denoted by A of this A of beta, and you can immediately check this is basically the collection of all, this is precisely in fact the collection of all polynomial expressions in beta ai in I. Okay. So, if alpha is integral over A, then this is, so this of course by definition contains I. So, this is a ring this is an extension of the ring A. So, the thing is, so if this integral over A, if equivalent to is finitely generated over A, the third condition, okay, maybe I should just, the third condition here simply says there is a subring. So, there is a subring C of B containing A containing A alpha, there is a subring of containing A alpha. So, that is we have the situation that A is contained inside A alpha is in C and C is further subring of B. So, there is a subring which is finitely generated. So, this subring is finitely generated over A. Okay. This is the third condition, and then we do have the fourth one. Fourth one, let me write it here because the definition is already clear to you. I should simply let me put this one only. The fourth one says that determinant of alpha minus m is 0 for some square matrix M over, okay, or this is in other words, this is an eigenvalue, alpha is an eigenvalue of the matrix M. Okay. So, these are going to be equivalent, we will prove. Okay, so before that let me just quickly remind you what it is that earlier determinant functions we have defined it over over any fields which do have certain geometric interpretations, and then purely algebraically we can define determinant of a matrix by a formal expansion, namely the summation over all permutations, then sign of the permutation times some some product of elements of the matrix. So, that definition, that is this wholly algebraic definition, that is valid over any commutative ring as well. Okay. So, what I mean is, using that expression we can define the determinant of any matrix over matrix with entries from any commutative ring, the same definition, and therefore the properties of determinants that follow directly from the definition, those properties will hold, these properties will hold even in this general setup of any commutative ring. Okay. For example, if let us say that if the columns are having some dependencies, then that will result in vanishing the determinant. So, all this whatever properties in the field that we could prove from just from the definition, those properties will be valid here as well. Okay. So, now let us try to prove this four statements. How to do this proof? So, first of all, from 1 to 2, that is actually quite easy. So, A alpha, this consists of all polynomial expressions in alpha, right, and A is integral over A, that means we do have a monic polynomial with coefficients over R whose root is alpha, and therefore alpha n will be a combination of some combination of 1 up to alpha to the power n minus 1 from that polynomial relation that alpha satisfies. Okay. So, therefore, in any such polynomial alpha to the power n, all these alpha to the power n and any bigger power of alpha can be immediately substitute in terms of, can be immediately expressed in terms of lower powers of alpha, namely up to alpha to the power n minus 1. So, therefore, you can see basically any such polynomial expression in alpha actually becomes a combination of 1 up to alpha to the power n minus 1. Okay. So, that proves that 2 is 2 holds when 1 holds. Okay. So, this is done. Again let me tell you that the idea is replace higher powers of alpha by the smaller powers of alpha, and that is exactly possible because alpha satisfies some monic polynomial, okay, over A. So, 1 implies 2, now let us talk about 2 implies 3. So, for 2 implies 3 we can simply take C to be, so this is trivial, take C to be A alpha itself, okay. Now we have come to, we have to prove 3 implies 4, we have to prove 3 implies 4. So, we consider this map from C to C. So, homomorphism sending each x to alpha x, this is a homomorphism, right. Now, you see that therefore, so C is by by hypothesis C is finally generated over A. So, let this be a generating set, okay, generating set. So, therefore, alpha of x1 must be a combination of, so this is a generating set. So, yeah, alpha of x1 must be a combination of xi's. So, let me write at a11 x1 up to a1n xn. Similarly, you can do it with alpha 2, you just write it as alpha 2 x1 up to alpha to a2n xn, and that is how it goes, alpha xn will be something. Now, you bring everything to one side, what do you obtain? What you obtain is the following. Okay. What you obtain is the following, that this alpha minus a11 times x1 plus actually a12 x2 a1n xn is 0. Now, then a21 x1 plus alpha a12 sorry a22 x2 a2n xn is 0. Similarly, an1 x1, the last term there will be a alpha minus a nn xn is 0, okay. So, that shows if you define M to be this matrix whose coefficient is a11, a12, a1n, similarly an1, an2, sorry, an1, an1, an2, ann, then you see that like alpha I minus m times, okay, so I will finish it soon, this is going to be 0, right. Since this is a generator, therefore, all xi's cannot be 0. So, thus that means this has having a non-trivial solution, and another way to interpret that is the columns of this matrix have some linear dependence, okay, and that will result in the determinant will be 0. So, this results in determinant is alpha I minus f is simply 0. So, 3 to 4 is done, and from 4 to 1 is actually trivial, because if for some matrix this determinant is 0, then basically alpha becomes the root of the characteristic polynomial of M. M is a matrix over A. So, the characteristic polynomial of A, M by definition, this is the monic polynomial, right, with coefficients over the ring from which the M is taking its coefficients. So, therefore, 4 to 1 is even trivial. Okay. So, I think with that Okay. So, well, so thus we have 4 equivalent criterions for a matrix for an element to be integral, and I will just quickly tell 1 or 2 examples, and with that I will just I will finish. So already I have told you some examples, maybe some more along that line, or in fact I think for most for for the purpose of our course, though the definition has been given in the generality, but for the purpose of our course we can simply stick to this situation where A is Z and B is some subring of C. Remember that if B is a subring of C, then it has to contain 1, and therefore it has to contain all iterations of 1. So automatically any subring of C contains Z. That is clear. So if a complex number is integral over Z, then we say that an algebraic integer okay. What are examples of algebraic integers? So you see, so these are special cases of this general notion of integral over a ring. So of course root 2, root 3 or any nth root of n, these are algebraic integers. Roots of unity, and well, I think I will give rather more examples next time. Yeah, so as I said, well, today I will stop here. So for the purpose of this course, I mean it will be like if we wish we can simply stick to algebraic integers only instead of considering general notion of integral elements over A. But anyway, in the next lecture I will say a few more words on this, and then we will go for, then we will move for something else. Okay, so with that I finish this lecture.